Hey.
Hello, my dear. How's it going?
Oh, it's going pretty well. I'm excited because we have questions from viewers.
Yay, viewer questions. I love it.
I know, I always love when we have viewer questions. In fact, we have two great viewer questions from Kavya from Helsinki. So for the next two of my episodes, we will be answering Kavya's questions. So Kavya, thank you for submitting these questions.
I love it.
Mhm.
International
Yeah,
image analysis questions. How fun.
absolutely. And they're really good questions too, so I'm excited to talk about them. So you too, please submit your really great questions to Ask Erin, Dear Beth. We'd love to feature them on the show. Um, so Kavya's first question. I have been trying to implement QC on my cell painting images using features from Measure Image Quality. I've been using PCA on the measured features. I seem to have measured about 107, and it seems like one of my cell types is consistently different from the other based on local focus score features. What does this mean? How do I interpret what some of these features mean?
Nice.
Yeah. And that's a great question because what do features mean in general can be really difficult, but it can be especially difficult for some of these things like image quality, and some of them get a little mathy.
Yeah.
Um, so when in doubt, I always start with going to the Cell Profiler manual. And this is the same exact information that's in the Cell Profiler module help. So if you pull up the Cell Profiler module help, you will find all this same exact text. It's actually built from the same exact thing.
Nice.
Um, So there's a few different kinds of quality measurements that Cell Profiler makes in Measure Image Quality. I'm going to start with some of the easier ones to talk about, which are not the blur ones that were in the original question, but just because it's important to sort of mention them. Um, the intensity metrics can tell you, again, like how much intensity is going on. And generally speaking, that's not going to be a problem, but these are great metrics for seeing if some of your images are really different from the others. So maybe they have a different maximum or different minimum, or maybe there's some accident of metadata going on and they're scaled differently. That would be potentially really dangerous. So these aren't ones that are going to be good for checking things like, is my image blurry? But they might indicate sort of overall problems with maybe you've accidentally mixed in some 8-bit images with your 16-bit images or something like that. Um, Threshold metrics. So thresholds, Cell Profiler can calculate the thresholds as part of the measure image quality module for a bunch of the different thresholding methods that it uses. And again, no individual threshold is wrong, but it can help you see if there are patterns where the thresholds are consistently different between, for a particular set of images, where is the threshold being set? Saturation metrics. So um, what fraction of the images of the pixels in your image are either the maximal possible value or the minimal possible value? Because if you're at the ends of the spectrum, you're no longer measuring quantitatively, right? And
Mm.
so at that point, like there could be lower signal or higher signal, and you've lost the ability to detect it. So trying to keep as little of your image as possible above the camera maximum or below the camera minimum, helps make sure that, you're always in a quantitative range when that's important.
Yeah. Yeah. It can also be the intensity metrics and or saturation percent maximal. Found those really helpful for when there is some amount of debris, like fluorescent
Mhm.
debris in an image that accidentally, you know, particularly fibrous sweater dropping onto your sample someday, will often be
Mhm.
easily flagged. The images that have, some chunk of very fluorescent, something that's not supposed to be there will
Mhm.
often be easily flagged by those metrics.
Yeah, great point. Um, And the last set of metrics are the blur metrics. So blur can be kind of difficult to define. So there's a few different mathematical approaches that are here. One of them is saying what is the correlation within particular areas. So if I take a square of 50 pixels, how likely is it that all the pixels are the same, like are highly similar? Um, because real biological objects probably have a lot of variability if they're in focus. If they're not in focus, they might have more sameness
Mm.
because they're out of focus.
Mm-hmm.
And so increased correlation can actually mean that your image is blurry. Um, um, the focus score sort of operates on a similar principle. It actually operates based on how much is the variance in the image. The idea being if your image is blurry, if the amount of like variance across the image is very little, probably something is wrong. It's not in focus because real biology sort of jitters.
Mm-hmm.
Um, and there's some great citations here for a bunch of these. That one, they actually compared a whole bunch of different methods across a whole bunch of, oh, wrong paper. No, no, something went wrong, of course. Um, they actually tried a whole bunch of different methods, and then they tested
Ooh.
them across DIC images and bright field and fluorescence and a whole bunch of things, and actually were able to say like across all kinds of different um, things, the like this particular method often produces really good sort of measurement of blurriness. Um, so that is what Cell Profiler refers to as the focus score. The local focus score is just that and do it in tiles. So this is the particular metric we were asked about. Um, so, if I break the image into tiles, maybe, parts of it are in focus and parts of it are out of focus. Um, and so we can say, what is that focus score across the whole image? And then get the focus score for each and take the average.
Mm. Mm-hmm.
There's also the power log slope, which I won't go too deep into the math for, but basically it goes into the frequency space of the textures of in the image, and then takes the log of a couple different metrics, and you say, what is the slope of these particular lines of measurements in frequency space? If you think back to your Fourier optics, high intensity information or high sort of noise information is encoded in a different part of frequency space than like big patterns. And so the slope of this line actually helps indicate, what actually, if the image is changing a lot, if the textures change a lot, or if the textures are actually pretty smooth.
Mm.
So the slope of that line changes. Um, so Um, CellProfiler provides you all of these. And I want to call out this paper in particular, which is from the imaging platform from a bit ago now, from 2012, that goes through some quality control workflows. And they actually did a really lovely job doing some things with synthetic blurring, as well as taking some images and then like physically, figuring out the right focal plane and then going 32 microns below and 32 microns above to actually do a bunch of measurements to say, well, like, how far out of focus can we be before we start losing our ability to detect like our quantitative measurement and things like that, and measuring a bunch of these cell profiler quality metrics in these different conditions. So this is a really nice paper. Um, and we in fact have, and we'll put a link in the show notes, a tutorial for looking at image quality for in Cell Profiler that sort of uses some of these measurement quality metrics. But a couple of things that I want to point out are just that generally speaking, when you are doing these, it's hard to draw hard cutoffs. It's hard to say like one of the sort of counterexamples to that is you might be able to draw a hard cutoff and say if more than 2% of my images is saturated, I think there's too much saturation. I can't get good quantification of intensity from here. I don't want this image anymore. But for things like blurring and things like correlation, especially channel to channel, these things can be really different and certainly experiment to experiment, and they can be affected by things like confluency, because that will change the amount of intensity variation in your image. So usually we're not so much looking for a hard cutoff as we're looking for the outliers.
Mhm.
Um, so this is some cell profiler analyst data from the cell profiler quality control tutorial. And here we're looking at one of the image quality metrics, which is correlation in the ER channel at a scale of 20 pixels. Again, the higher this number is, the more likely we think there might be a focal problem. And so we can check a really low image. For some reason, all of these look bad in linear scale. That looks indeed like a perfectly fine image. And then something with a really high value,
Mm.
that indeed looks like a blurry image.
Yeah,
One,
totally.
one, uh, one cannot deny that that image could be better. But here's the next highest one, and this doesn't strike me as terribly blurry. There's a sort of out of focusy guy or like piece of debris there.
Hmm.
Let's check the other one. But so this is where I say, it can be really difficult to define exactly what's the cutoff because this is the second highest well, and
Hmm.
this is fine, but this one is clearly not.
Yeah.
And to my point about um, channels, so here, for example, is that power log slope metric across two different channels, the nuclear channel and the Golgi channel. And the first thing I'll draw your attention to is just the scales of these are different. And even like this central blob here is not like perfectly on a diagonal. There is some scatter around here that the power log slope in one channel versus the other might be different.
Hmm.
We can look at some of the outliers here, um, and say, yep, this image sure looks terrible. It's, basically empty. So clearly this is a bad image.
Hmm.
Um, but some of these, um, they might um, just be, perfectly analyzable, but a little bit empty. Or they might have a different metric just because of a little piece of debris that's off to the edge
Hmm.
that wouldn't, for me, say, I'm totally uninterested in this image.
Yeah.
Um, I would just say maybe I want to mask that part of the image out. And it's hard, right? Because we always want to try to figure out how we can keep most of our data in. Nobody takes data just so that they can throw it away.
Yeah.
Um, that's not why we spend all of this time sort of lovingly doing all these experiments only to throw them away. Um, so uh, I just want to do one more here. Oh, I didn't mean to move that. Which is to show the one that Erin mentioned, which is percent maximal. Because that we can definitely use to find things like debris.
Yep. There we go.
That's a big old piece of debris.
That should not be there.
Um, but these metrics can all help. They can certainly be used to find things, but they can be really hard to sort of set hard limits on. You can certainly decide to sort of say, I'm going to make a central clump based on some metrics that I've checked in my data. But for things like how consistent is the data for different channels might be really different for a nuclear channel where we know it's not going to be fully confluent, and a cell membrane channel where we know this, if the cells are fully confluent, there will be no background present in the image.
Mhm.
So we should be careful about setting hard cutoffs, and we should be careful about sort of overly relying on these metrics, because they can be really hard to interpret. But used carefully, they can help you identify some of the real problems in your image, And if you do the cell profiler quality control tutorial, you can see how you can create classifiers to throw them out if you do find hard limits that work for you for your particular data set for your particular day.
Yeah. I think also what I found really interesting is I think okay, this is, over time, how we have used these QC metrics has changed. I think some of that is uh, changes in the field, and some of it is changes in the microscopy, right? So we've found like the data sets that we are given now are often have less debris and focus issues than they used to, right? Like just autofocus on microscopes is better than it was in 2012, right? Like things have changed technology-wise there. So we are much less likely to get a giant set of images in which there is a systematic focus issue, meaning we are less reliant on actually pulling out bad images from our data. And I think we have also sort of moved then a lot further from whole image rules and QC and filtering into looking at the single cell level and saying, okay, I've got some single cells, like at the cellular level, where my measurements are crazy far off. And maybe it's because, oh, this cell was totally out of focus, or this cell was underneath a giant piece of debris,
Mhm.
and filtering that way. But that requires a level of compute that again, was totally different in Access in 2012. And so um, even not that I joined the lab in 2012, but even when I joined the lab in 2019, right, what we do now as common practice versus then is still even
Mhm.
shifted.
Yeah. So all of that is a very long way to say I'm not sure exactly what the local focus score being different for a particular phenotype means for you. It could be something as different as it's changing the confluency. And so this metric which says how consistent is, a particular region in its intensity and then averaging that across the whole thing, maybe there are more regions that are empty or more regions that are full, and therefore we're changing this value. It could be something like that. It could be that it's changing the height of your cell, which is making it sort of be out of focus, like, or seem more out of focus, even though it is in focus. There's a lot of things that this could be. But there's a lot of ways you can use this data. It can just be a little hard to interpret. I
Yeah.
think that's everything I wanted to say about quality control.
Yeah, I think that's a great amount of information. And
Hmm.
we do have Ask Erin Dear Beth episode on like interpreting cell profiler features.
Hmm.
So there are certainly some that are very interpretable. But the QC metrics, as you mentioned, uh, are sometimes less so.
Hmm.
That doesn't mean they're not helpful. And I think in an interesting example of, right, you popped up the papers, they had lots of deep math in them. Like one does not need to understand the math behind these to still know how to use them or how
Hmm.
not to use them. That's definitely, but one can, if
Hmm.
you really want to, the math is there.
Yeah. And the
Um,
self-profiler manual tries to make it very clear how to use them without necessarily needing to sort of deeply study the equations.
yes, absolutely.
Great. Thank you so much for joining me on a viewer question. We'll have another viewer question coming up in an episode very soon.
Thanks for diving in with us, and thank you to our viewer
Hmm.
for writing in a question. To
Yeah.
all our other viewers, please ask us questions. We find them
Hmm.
exciting.
Yeah. All right. Talk to you later.